So we've seen how useful orthogonal bases could be. Do we always have such a basis? Well, it turns out yes. Any subspace of Rn has an orthogonal basis. And it's actually quite straightforward to go from a basis to an orthogonal basis. There's an algorithm that we use which is called the Gram-Schmidt algorithm. So you assume you have a basis, u1 to um, of vectors of W, and it's a basis of the subspace W. What you want is to build m pairwise orthogonal vectors that are each found in W. If you can do that, then you have found, by necessity, m linearly independent vectors in W. And because the dimension of W in this example is m, then we have automatically a basis for W. How does it work? It's very simple. First, you start with u1. That's going to be the first vector of your orthogonal basis. Next up, you're going to be building a new vector, the vector u2 minus the projection of u2 on u1. What does that look like? This is a projection of a vector on a vector here, not necessarily on a subspace, and this is a formula we had from way back when, which happens to be one of the building blocks of the projection formula on the subspaces, but let's see what it is. So let's say we have the vector u2 right here, and we have u1. So the projection would be this vector here. And we know that the perpendicular vector right here, that's u2 minus the projection of u2 on u1. But why is that useful? By definition, u2 minus projection u1 is perpendicular to u1. That's the notation we're going to use to talk about perpendicularity. A little t upside down, a little flipped up t. So u2 minus the projection of u2 on u1 is perpendicular to u1, which is good, but the crucial thing is that this vector is in the span of u1 and u2. Why is that the case? Well, look, u2 is in the span of u2, and the projection of u2 on u1 is some stretching of the vector u1. So what I have here is a linear combination of u2 and u1. So u1 exists, u2 minus projection of u2 onto u1 is perpendicular to u1, so I've got the orthogonal part here, and they span the same set. u1 and u2 span the same set as u1 and u2 minus the projection of u2 onto u1. That's the basic idea. You keep on subtracting off projections onto the span of the preceding vectors that you obtain. And the result is an orthogonal basis for the subspace W. So here's the algorithm. You have a basis u1 to um. It's a basis of some subspace. We'll call it u. In your slide I called it W, but here it's going to be called u. So we need m vectors in order to have a basis for u, because u is an m-dimensional space. And we want them all to be orthogonal, pairwise. Easy, w1 will be u1. Great. And I'm going to create a new subspace v1, which is the span of w1. That happens to be exactly the span of u1. Because w1 and u1 are the same thing. Next up, I create the vector w2, which is u2 minus the projection of u2 on v1. Create a new subspace v2, which is the span of w1, the previous vector I had, and w2, the new vector that I found. W3 will be U3, so the original third vector, minus the projection of this U3 on the vector space V2, which we had found here as the span of W1, W2. And I'm going to set up a new space V3, which is the span of W1, W2, W3. You continue this way until you get to your last vector Wm, which would be Um, the last vector in your basis, minus the projection of on the preceding subspace Vm minus 1, which, even though it's not explicitly written here, you can recognize as being the span of W1, W2, all the way up to Wm minus 1, and you'll set Vm as the span of these vectors, the m vectors. Then U and Vm are the same spaces, so you haven't changed the space, but W1 to Wm is now an orthogonal basis of U, not just a basis. Now, if U was orthogonal to start with, this process doesn't change the orthogonality relation. But if it wasn't, now we still have a basis with the added bonus that it is orthogonal. And formally, this is what it would look like. Like, instead of computing the projection on the subspace, you just apply it directly. So W1 would be U1, W2 would be U2 minus the projection of W2 on W1, W3 would be U3 minus the projection of U3 on W1 minus the projection of U3 on W2, and so on until you get to Wm, which is Um minus, and then you'll have a sum of m minus 1 projections. You're always projecting onto one of the preceding vectors that you obtained, wi's. At the end of the day, this set is then an orthogonal basis of U. If you need an orthonormal basis, then you just make sure you take all of your orthogonal vectors and you divide them by their lengths. And that gives you an orthonormal basis. At each step of the way, the vectors in the spanning set for the subspace Vk are orthogonal by construction, so it's pretty easy to compute the projection onto the next span. And in general, you see that the span of W1 to Wk would be the same thing as the span of U1 to Uk. Now, this is something you could work on. You could apply the algorithm, the Gram-Schmidt algorithm, not just on a basis for you. You could use a spanning set for you. So there might be some redundant vectors in there. And the idea is that the Gram-Schmidt algorithm would sort of filter out the redundant vectors, right? Whatever you get at the end of the process, W1 to Wn, which is not a zero vector, that forms the orthogonal basis for you. So, using the Gram-Schmidt algorithm, can you find an orthogonal basis for the subspace W, which is the span of 1, 0, 0, 1, 1, 1, 1, 0, 2, 1, minus 1, 1? Sure. We start with this. First of all, we should verify if it's a basis or not, but we don't actually need to verify because, as I've said, if it's not a basis, when we go through the Gram-Schmidt algorithm, some of the vectors will be the zero vector, and we can just ignore them. So we don't even need to verify if this thing is a basis. It is. Sorry, not the span, just the three vectors here. It is, but we don't need to verify that. So we start with the first vector. So from our perspective, this is going to be U1, U2, U3. So we start with the first vector and call it W1. That's 1, 0, 0, 1. Great. The next step then is to compute U2 minus the projection of U2 on W1. And then we have a formula for this. We just need to find the Fourier coefficient here. That's the Fourier coefficient right here. So you would have U2 minus the inner product of U2 with W1 divided by the square of the length of W1 times the vector W1. And we know what these are, right? This would be 1, 1, 1, 0 that's the vector u2, minus, again, u2, 1, 1, 1, 0, dot w1, which we'd found in the previous step. Reminder, it's exactly the same as u1, but, so there it is. So 1, 0, 0, 1 divided by the square of the length of 1, 0, 0, 1, and then you multiply by 1, 0, 0, 1. One thing you might want to use as a trick is if you've computed this length, set it aside, store it somewhere on a piece of paper, because every subsequent step is going to require this computation, at least the 10001 squared, or the square of the length. And you multiply that by 1001. So here you have a 4-dimensional vector. This here is going to be a real number, a scalar. You're going to divide it by this number here, which will be 2, right? 1 squared plus 0 squared plus 0 squared plus 1 squared. And you multiply that real number by the vector 1001. And what you get is 1/2, 1, 1, minus 1/2. Now, as a safeguard, you should take the time to verify that this W2 that you just computed is indeed orthogonal to the previous W1. It should be, but perhaps you made a computational error. So take the time to compute the dot product between W1 and W2, and you'll see that, yeah, sure enough, it's equal to 0. So they're orthogonal. The next step then, compute W3, which is U3 minus U3 dot W1 divided by W1 squared, at least the length of W1 squared, and you see it shows up here again, times W1 minus U3 dot W2 divided by the square of the length of W2. So both of these numbers here, these things are numbers multiplied, or scalar multiplication with the vector W2. I'm not writing out the details, it's just computations. I want you to do them. Don't just take my word for it. And you're going to get this following expression. 2/5, 1, 2, minus 3, and minus 1. And so that will be your W3. What you get out of this is that the Gram-Schmidt algorithm gives you 3 orthogonal basis vectors. They're all different from 0, so the original set was a basis. It means that W is a space of dimension 3. Now you can simplify the calculations by scaling the W. And here, this is an instance where scaling makes sense because you're trying to come up with a basis. You're not trying to come up with the actual projection itself. You're using the projection to come up with a basis. But once you have found the basis elements, the vectors in the basis, then you can rescale them as you want. And rescaling them could help you remove some of the less savory fractions. It is also orthogonal, as you can easily verify by doing the dot products of all of the pairs. Do it if you're not sure. If you wanted to get an orthonormal basis, you would take these vectors and you'd divide them by their lengths. So the length of 1, 0, 0, 1, the square root of 2, the length of 1, 2, 2 minus 1, square root of 10, and the length of 1, 2 minus 3 minus 1 is square root of 15. If you don't know how to do this, you need to figure it out. It's easy, right? You just compute the square root of the sum of the squares of the constituents. So this is an orthonormal basis. Now you'll notice the scaling factors matter because in orthonormal bases, you're not just finding orthogonal linearly independent vectors, you want each one of them to have length 1. So you do have to keep the scaling factors in front of them. So how would we find the best approximation, say, of the vector v, which is 1, 2, 3, 4, in the subspace w, which is spanned by these things here? Well, is it the case that v is in w or not? No, I mean, it's not in w, right? And this is one thing we'll find. Even though it says find the best approximation to v in w, I mean, find the best approximation in w of the vector v. So W is spanned by 3 vectors. You recognize them as the same 3 vectors from the previous set. So let's call them n1, n2, and n3, these vectors. And we've already shown in the previous exercise that they form an orthogonal basis of the subspace W. So if I'm looking for the best approximation of the vector V in the subspace W, I'm looking for the projection of V in or onto the subspace W. So I need to compute the projection of V on W, which according to the formula that uses the Fourier coefficients, it's going to be V dot N1 divided by the square of the length of N1. That's a real number. You multiply that by the vector N1. And then you add to that V dot N2 divided by the square of the length of N2. Again, a real number multiplied by N2. And you add to that V dot N3 divided by the square of the length of N3. Real number scaled or multiplied with N3. So V is given in this specific problem, 1, 2, 3, 4, dot N1 divided by, anyway, you see it here. I'm not going to say it, but it's there. And then you just need to do the computations. So you know what N1, N2, and N3 are. Put them in. You'll get a vector, you'll get another vector, and then you'll get a final vector. Each one of these has 4 components. As a reminder, this bit is a real number, this bit is the vector. This bit is a real number, this bit's a vector. Real number, vector. So you have a sum of 3 vectors, and their result is a vector, the vector 1/3, 8, 1, 3, 7. That is in W. You see that it is not the same thing as 1, 2, 3, 4, but it's not that far from it either.